Today we will discuss two important topics. Module 5. First one is the Newton-Raphson method, and the second one will be the Lagrange interpolation method. So basically, the Newton-Raphson method is for solving the transcendental equation, for solving the value of x, and the interpolation is for finding a unknown value. Also, coming to the Newton-Raphson method, this is an important method. So we have an f of x is equal to 0. So let you assume that the x0 is the solution for f of x, or it is an approximate value. X0 be an approximation for the root f of x. So when you apply x0 into this equation or the given equation, you will get a reasonably satisfying answer, but it's not the correct answer. So let x1 is equal to x0 plus h. So a minor increment or decrement with respect to the x0 will give you the correct root. X1 is equal to x0 plus h be the correct root, so that f of x1 is equal to 0, the real root. Expanding the f of x1 is equal to f of x0 plus h by the Taylor series we get. We're expanding the terms. So it's f of x1 is equal to f of x0 plus h is equal to f of x0 plus h into f dash of x0 plus s square by 2 factorial. You know this Taylor series. So neglecting the higher order terms, like after the x0 s square, so neglecting all these terms for small values of h and neglecting the terms of s square, f cube, etc., we get f of x0 plus h into f dash of x0 will give you the new value. So that gives you the new solution f of x0 plus h into f dash of x0 is equal to 0. From this equation, take the h. So h is equal to minus f of x0 by f dash of x0. So we know that x1 is equal to x0 plus h. So replacing the values, substituting for the h, we have h is equal to x1 minus x0. So rearranging the equation, we have h is equal to x0 minus f of x0 by f dash of x0. Proceeding like this, we can get the successive approximations of x2, s3, xn1, xn plus 1, etc. So we know that increment, how that increment is written or converted to the Taylor series, and how we can get approximated the values. So the successive approximations in the case of Newton-Raphson method is given by this formula: x n plus 1 is equal to xn minus f of function of xn divided by f dash of derivative of the xn for n equal to 0, 1, 2. A little bit theory into that. If the approximation xn1, xn plus 1 used by 3 converges, provided that the initial approximation s0 is chosen sufficiently close to the root of f of x0, f of x equal to 0. So the convergence depends on the choice of x0. If x0 is very near to the real solution, you will get a fast convergence. Convergence of Newton-Raphson method is similar to the iteration method, which we have discussed in the last class. So we have phi of x, new function is equal to x minus f of x by f dash of x. Differentiating this equation, With respect to x, we have phi dash of x is this value should be less than 1, the modulus value. And we get on the RHS we get 1 minus expanding this differentiation, we get like this, and it should be less than 1. Simplifying, we get for convergence of Newton-Raphson method, we have modulus of f of x into f double dash of x should be less than f of x square. Okay, so this is about theory. You don't want to study detailed theory, but for your basic understanding, I have shown that. Coming to the problem, this is very important for you. You have to find the root of x sin x plus cos x is equal to 0. Find the root of x sin x plus cos x is equal to 0. So by seeing this equation, we understood that this is a transcendental equation, as this equation is having the trigonometric values, as well as when you make it to a non-zero equation, that means x sin s is equal to minus cos x. So both the LHS as well as RHS is having a x value. So it is a transcendental equation, and you have to solve by the Newton-Raphson method. So you have the f of x given by x sin x plus cos x. Differentiating this one, you know that cos x will uh, come to sin x, and then x causes minus sin x is equal to by this sin x will be get cancelled, and the x cos x will be the derivative of the f of x. So we got the values which we require for solving the approximations. Okay, like this. Coming back, yeah, we have the Newton-Raphson method formula given by x n plus 1 is equal to xn minus f of x divided by f dash of x. So that is the formula you have to remember for solving the problems by the Raphson method. So we are assuming that the or we are taking x0 as a pi value. So x0 we are taking as a pi. On this assumption, we have x1, the new approximation. So when you are applying the pi value to the f of x, you will find that the value is very near to the convergence value. It won't be an accurate value. So we need the accurate value. So to find that plus h, what is the increment you require? You are going for this x1 is equal to x0 minus f of x divided by f dash of x. Same equation, you are applying the value. You got 2.8233. You will keep on repeating. So the new value of x0 or the x1 will be 2.823. So you get x2. X2 will be like the 2.8233 minus. You can instead of this 3.1416, you have 2.823. Okay, so that equation will be there. So by repeatedly doing this, uh, like the iteration, you will end up with a converging value of, here you can see, up to the fourth digit, 2.7984, 2.794. So that means there is no plus h or no increment between the last two values. So this is the converging value. So therefore x is equal to 2.7984 can be taken as the root of the equation x sin s plus cos x. Basically, we are decreasing the plus or h value so that we get the solution. I think it's very clear for you. Similar problem for a better understanding. Find the smallest positive root of x minus e raised to minus x is equal to 0 by using the Newton-Raphson method. So coming to the solution, we have the function f of x is equal to x minus e raised to minus x, f dash of x is equal to 1 plus e raised to minus x. Then when you put f of 0 in the main equation, you will get the value as minus 1. And when you put 1, you will get the value as 0.63212. So by these initial values, we find that, or we understood that the smallest positive root of f of x is between 0 and 1, because the value is changing from a negative value to a positive value. So that means the root is in between, the method of false position. Okay. So let x0 is equal to 1. We're taking, assuming that f of x is 1. Okay, so we got the initial value, which is very important in the Newton-Raphson method. So okay, then to the problem, Newton-Raphson method formula is given by xn plus 1 is equal to xn minus 1 minus f of x by f dash of x. So yeah, so when you apply the values, f of 1 you got as a 0.63212. So we have x1 is equal to x0 minus this equation. So we assume that x0 is 1. So 1 is here. X0 1 minus e power minus x0. So you will get 0.5379 as the new x1 value. So we got a difference of almost uh, 0.07. 0.1 approximately you got the difference. Yeah, 0.1. So this h value. So again you will repeat with we will restart with the new value was 5.5379. So we'll put yeah, when you're applying this value 0.5379, you are getting a value very near to 0. So this is not the exact root. There again you are doing the process and you're finding the x2. So you have the new value, new x1. X2 is equal to x1 minus f of x by f dash of x. You got 0.567. So even between these values there is a 0.03 difference. So this can be continued for a better approximation. So you can for in this case they have just yeah, for even s3 value also they are getting, or we may get the value as 0.567. That means there is a convergence in the third digit. So that tells that the solution or the root of the equation x minus e raised to minus x equal to 0 is given by 0.567, and it is based on the assumption that we have to take the value correct to 3 decimal places. So that's about the Newton-Raphson method. And the last topic of this module 5 is a different one, interpolation. Interpolation, as I told, it's about finding the missing values. So suppose you have used these interpolations while doing your structural design by using IS code for uh, designing the concrete structures, as well as you will use it for the design of steel structures also. So you may have a big table which have values at only on important salient points. So if you need to find the values for the points between those points, you have to interpolate it. That's the requirement of the interpolation, and also it can be used for forecasting the values out of the boundaries. So basically, we are studying only the linear interpolation function, and we have for second order for quadratic Lagrange interpolation n is equal to 2. We have g of x is equal to fi into bi of x, ranging I equal to 0 to 2. So g of x is equal to, this is the equation of interpolation. G of x, the function, interpolated function, is equal to f0 into b of x plus f1 into b1x plus b2x. So these are the functions, individual functions, and These functions are combined with the B0 interpolating values to get the interpolation equation. So for the second order n equal to 2, you have the equation V0 is equal to. So this equation has to be studied for solving the problem. It is like x minus all the top numerator is subtracting from the x value x minus x1 into x minus x2 divided by x0 minus x1 into x0 minus x2. Similarly for b1 of x, only the denominator changes to x1. Then for b2, you have the x2 here. Okay, that we have studied here that the interpolation function that the given function f0, f1 and f2 is modified with the b0, b1, b2 terms to get the interpolation equations. Okay, coming straight to the problem, we have the given datas f0 is equal to 1, f1 is equal to 2, and f2 is equal to 4. We have the x0, x1, x2 values given here. We're supposed to find the quadratic interpolating function g of x. So for solving this problem, I have to remember the equation that we have learned just before. That is the g of x is equal to f0 into b of x plus f1 into b1 of x plus f2 into b2 of x. So we are supposed to find the b0x, b1x and b2x for relating the f0 and the g of x. So the Lagrange basis functions they are called. They are given by the equations are shown on the right: b0, b1, b2. So we have the x1 value as 4. So x minus, when you compare with this, x minus 4 into x minus 5 divided by it is x0. So 3 minus 4 and 3 minus 5. Similarly, the b1 of x is x minus x0 into x minus x2 divided by it is subtracted from x1. That's why we have 4 4, and similarly the b2 of x. So this is the Lagrange basics function which is required for converting the function to the interpolation function. So the interpolation function g of x is given by g of x is equal to as per the equation, yeah, f0 into b0 of x plus f1 into b1 of x. So we have 1 into b0 of x plus 2 into b1 of x and 4 into, yeah, b2 of x. Hey, yeah. Coming to the condition of the third level, there is cubic Lagrange interpolation. So as the order of interpolation is going higher, from n equal 2 to 3, so this will be a good interpolation equation compared to the previous one. So this shows a very accurate value. So coming to the problem, consider the following table of functional values generated with f of x is equal to ln x. So we have the function f of x is equal to ln x, and for different values of x, 0.4, 0.5, 0.7, 0.80, you're getting the corresponding values of fi as like this. So when you see through these values, 0 0.4, 0 0.5, yeah, 0.6 is missing here. So by this interpolation, we are supposed to find the value of 0.6. Just right. So find g of 0.60. So from here we can assume that, or we can identify that the value will be within or between this value, because as the 0.5 value is minus 0.69 and 0.7 is minus 0.35. So the value will be in between, mostly it will be a half of this value. That will depends because the variation depends. So even yeah, it will be in between these two values. That's our primary assumption. And we have g of x is given by the main equation, that is f0 into, so this equation has to be studied. The When you compare with the previous equation, you can see yeah, x is common in the numerators and x0, x1, x2. Similar to that, when you can find x is common in all the numerators, and denominators you have x0, x0, x0 for the first one, x1, 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 x2, 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 and x3, x3, x3. So this will be uh, easy for learning this equation, this concept. So we got the equation. So this is the interpolation equation. So this equation has to be directly substituted to get the g of x value. So we have the equation I have shown on the right side for the comparison. Yeah. So this is clear for you. There is no need to have a doubt for this. Directly applying the values, and by employing all these values and getting added, you will get the value of g of x0 is equal to 0.50. It is correct as per assumption. It is between the minus 0.69 as well as minus 0.35. So that's about the second problem, or the last